Welcome back. Now we're going to calculate things about acids. What we learned is what an acid is. It gives off H plus in solution. What a base is. It gives off OH minus in solution. And how to name the acids and bases. Sprite is delicious and all that good stuff. Now we're going to try to figure out what is in the solution. If we have pure water, if we just got ourselves a beaker of water, is that acidic? Is it basic? Are there H plus in there, or is there anything in there that we need to worry about? And so the first thing we're going to do is try to figure out what's inside that beaker of water. Well, it turns out that water can do this funny thing, and it can react with itself. When it reacts with itself, one of the things it can make is H3O plus and OH minus. And you'll notice I used a double arrow here. That double arrow means both things are present. It's not a complete reaction. It doesn't completely run to the right. But when it's done, there's still water present, but there's also these products present. So even in pure water, there's actually a little bit of H plus and OH minus that are present, even in pure water. We call this an autohydrolysis reaction. It's a very fancy sounding name. But how much is present there? Well, people have done some work, and they said, hey, look, the concentration of H plus, and you'll notice I wrote this with H3O plus, and then I wrote H plus over here. Is that fine? Yes, because the meaning behind H3O plus and H plus is exactly the same. They are interchangeable in meaning. I couldn't write H plus on the right here in this reaction, because then my waters wouldn't balance out. I wouldn't have a balanced chemical reaction. But when I'm just talking about H plus and things like that, I can figure it out. Then, what's this other little thing I drew? I drew brackets around here. And by the way, I'm really bad at drawing square brackets. They should be very nice and perfectly square, but it's just not my strong suit. You'll find my end brackets tend to look more like the number 3 than anything else. Just be aware these are nice square brackets. What does this mean? This means concentration in units of molarity. So when you see that bracket notation, I say bracket H plus bracket, how you read that out loud, you say the concentration of H plus. So that's just a shorthand for the concentration of H plus. And in pure water, it is 1 times 10 to the minus 7th molar. Very small number. There's not a whole lot of H plus in pure water. 1 times 10 to the minus 7th molar. Now, if you were to guess the OH minus concentration in pure water, what do you think it would be? If we look at this reaction, water reacted with water to make 1 H3O plus and 1 OH minus. So if we have 1 times 10 to the minus 7th molar H plus, what do we probably have? 1 times 10 to the minus 7th molar OH minus. And we read that as the concentration of OH minus is 1 times 10 to the minus 7th molar. So those are our concentrations. Now I'm going to do something next that doesn't really make much sense, and it doesn't really make much sense actually any point in this class because we don't discuss where this comes from, but there's some really cool chemistry that you can do that you do when maybe a second semester general chemistry class that says, hey, what if I take that H plus and I multiply it by the OH minus? And again, those are square brackets even though they don't look particularly square. So I've got 1 times 10 to the minus 7th times 1 times 10 to the minus 7th. If you plug that in your calculator, you should get 1 times 10 to the minus 14th. Why is that number useful? Well, it turns out that number is useful because it is a constant. And a constant we call Kw, which is the water product constant, but it's just a constant. No matter what we do, no matter how much acid we add to a solution, no matter how much base we add to a solution, if we take the H plus concentration and multiply the OH minus concentration, it's always the exact same number. This is kind of like our gas laws. When we said P1V1 equals P2V2, we said, hey, look, they're the same at the beginning, the same at the end. And so we multiply them together and they're equal. Similar type of concept here. When we multiply H plus and OH minus concentrations by each other, we always get 1 times 10 to the minus 14th. What does that allow us to do? Well, it allows us to be able to solve for either one of these if we have the other one. So if I wanted to solve this and I said, oh, what's my H plus concentration in a solution, if somebody told me the OH minus, then I just divide this equation, both sides. Let me write it here, H plus times OH minus equals Kw. And then I divide both sides by OH minus to get my H plus all by itself. My OH minuses cancel on this side, and I get that H plus is Kw over OH minus. And remember, Kw is just a number. It's 1 times 10 to the minus 14th over OH minus. All right. So that's how we can calculate H plus knowing OH, or we could do the math the other way around, and we could calculate OH minus knowing H plus. And you might think to yourself, well, why would you need to know that? And sometimes we do. Sometimes we really need to know a lot about the acid-base chemistry in a system, especially in physiological systems. Our body and all the things that work in it are extraordinarily sensitive to changes in pH. The proteins that we have in our body can lose and gain protons with very small changes in pH. And that actually helps some of our body processes work. But if you do it wrong, then you can hinder some of those processes. So knowing a lot about H plus and OH minus concentrations is actually critically important for understanding the physiology and the physiology of a lot of how our bodies work. So as an example, if we know that the concentration of H plus in a solution is 1.0 times 10 to the minus 5th molar, and we want to know what is the concentration of OH minus in that solution, then we can just solve this equation. If you did that, you should get the OH minus is Kw over H plus, which is 1 times 10 to the minus 14th over my H plus concentration, which was just given to me as 1.0 times 10 to the minus 5th. And then I just put those in my calculator, making sure to use the built-in scientific notation in my calculator. If you're using your calculator wrong, you will get very wrong answers in this situation. I encourage you, pause this video, go find your calculator, grab it out of your backpack, bring it back over, and make sure that when you type this into your calculator, you get the number that I get. And the number I get is 1.0 times 10 to the minus 9th molar. All right, so a few things. One, Professor Clements, you always tell us that whenever we're doing stuff, we need to make sure to have units on everything. Why didn't you put units in here? The answer is a bit complicated, but this is one of those situations where we actually don't have to put units as we work the problem, but we absolutely, absolutely, absolutely must put units when we end the problem. I'm not going to go into the reasons why, but there's some good mathematical reasons why. If you put molar down here, I have no problem with that. And that's just fine, even though it doesn't really look like it gets you the right answer in terms of concentration at the end. So, is that what you got when you typed it into your calculator? If not, let me show you what I'm going to be typing into my calculator. I'm going to go ahead and type 1.0. I'm going to use the built-in scientific notation. So I pressed second, and I pressed my little x to the minus 1 key, and my calculator said E. I don't know if you can read that. 1.0 E, and I got minus 14 divided by 1.0 E minus 5. Okay, so that's what I got in there. Can you see that? You can see the last half of it. Now, I used a 1.0 for the number on top. Doesn't really matter. We're going to treat this number up here as exact. It turns out it's not exact. It actually changes quite a lot with temperature, but we're going to treat it as exact for this class because it makes our life a little bit easier. And boy, when I type that in, my lovely little calculator tells me this number, which doesn't look a lot like the number that I wrote down, which is 1 times 10 to the minus 9th. And you'll find that if you're using one of these TI calculators, they're great calculators. They're almost indestructible. They're really cheap for these particular ones, but they have a problem. And their problem is they don't know when to stop using decimals and when to start using scientific notation. So here's this number, and if you counted out all the zeros and did your conversion to scientific notation, you would get 1 times 10 to the minus 9th. The only problem is if that next number wasn't a 0, you'd have no idea what it is. So I'm going to show you something right now, only need to know it if you have a TI calculator. Most Casios and other brands do this a lot better than the TI calculators do. But what happens if you get an answer like this and you need another digit? The answer is not just to put a 0 there and be like, oh, I know it's 1.0 times 10 to the minus 9th. I put that there because I happen to know it is. But you want to actually be able to see that next digit. So what you're going to do is you're going to change the mode of your calculator to display everything in scientific notation. And then you can see all the little digits. So if I'm in my calculator here, I'm going to press the second key. Then I'm going to press this one here that says DRG. It brings me up a little menu that says flow, psi, and eng. I'm going to use the arrow key to choose psi, and then I'm going to hit enter. And now you can see it just tells me it's 1 times 10 to the minus 9th. But if I changed my numbers slightly, so I had 1 times 10 to the minus 14th divided by 1.03 times 10 to the minus 9th, if I still had it, oops. Oh, no, there we go. If I had a slightly different problem, sorry, that took me a second, and I had 9.99 times 10 to the minus that, it would still give me 1 with no things after there. But if I change it over, I notice there's lots of other digits there. There's the 1s and 0s and things like that. So we really can miss digits if we don't know how to use our calculator correctly. When you're done in scientific notation mode, I highly encourage you to switch it back. So you press second, you press the DRG, and you go back to floating point mode. Makes your life a little bit easier. Don't leave it in that mode, because then it'll display things like 20 as 2 times 10 to the first, and you'll miss that half the time and write down 20 wrong. So there we go, 1.0 times 10 to the minus 9th molar. When we have a final thing and we're trying to get a concentration, we have to put those units of molarity on there. Absolutely important that we do it. Significant figures. Since we're treating this top number as exact, our sig figs in one concentration is going to match our sig figs in our other concentration. And so we can rest assured that we have 2 sig figs in our ending concentration because we had 2 sig figs in our beginning concentration. All right, here's one for you to try. We have H3O plus in a solution is 1 times 10 to the minus 4th molar. What is the OH minus concentration? So pause, write this down, actually plug it in your calculator, see if you can figure it out. All right, H0 plus, what's that? It's the same thing as H plus. Is 1 times 10 to the minus 4th molar. We did the work in the other one to find that OH minus is Kw over 1 times 10 to the minus 4th. Kw is 1 times 10 to the minus 14th, and so you get 1 times 10 to the minus 10th molar. Again, put that unit on there even though it's nowhere else. And 1 sig fig here because we had 1 sig fig there. So H3O plus, H plus interchangeable. Make sure you're really comfortable with that because I do use them back and forth on purpose. Here's another one for you to try. What is the OH minus concentration of a solution when H plus is 2.3 times 10 to the minus 9th molar? So pause, try it out, come on back. You're back. So I'm assuming that you rearranged that equation and found out that OH minus is Kw over H plus, or 1 times 10 to the minus 14th over H plus in this case is 2.3 times 10 to the minus 9th. Plug that into your calculator. What I'm going to type in my calculator is 1e minus 14 divided by 2.3 e minus 9. And I get, again, a bunch of zeros in there, 0.000000. I don't want to count those. I'm going to switch over to scientific notation mode and get 4.34786 times 10 to the minus 6th. Lots of digits there. How many do we know how to keep? We've got 2 significant figures in this number, so we need 2 significant figures here. And we get 4.3 times 10 to the minus 6. Does that match any of our answers? Oh, it does. Yay. So we get answer A there. If you ever find yourself getting 10 to the minus 20ths, you typed it in your calculator wrong, you didn't use the built-in scientific notation of your calculator, and you need to go back and redo the problem. You should really only be getting numbers as small as about 10 to the minus 14th. Nothing smaller than that regularly occurs. It's possible, but it's not regular that it occurs. All right. Now, if you're trying to write a book and you're doing a lot of book about acids and bases and you know about these concentrations and it's like the 1800s and there's no computers, typesetting a concentration of 2.3 times 10 to the minus 6 molar is really difficult because superscripts, you don't really just have built-in things to typeset superscripts. So one of the things that people did is they invented a way to not have to talk about these concentrations using scientific notation because that gets a little bit tedious. And it really was just an invention of convenience. They said, hey, let's define this thing called the pH. And we're going to define it as the negative log base 10 of the concentration of H+. Very simple definition, negative of the log base 10. If you don't know how to do logs in your calculator, I'll go over it on the next slide, but that's what it is right now. So the pH is the negative log of H+. So if my H+ concentration was 1.0 times 10 to the minus 5th molar, I want to say my pH is going to be the negative log base 10. Most people don't write the 10 in. I'm going to stop writing it. Log usually means base 10, and in this case it does. And my concentration is 1.0 times 10 to the minus 5th. Plug that in a calculator. Your calculator is going to tell you 5. I'm going to tell you it's 5.00, and we'll talk about why in just a moment. But that's how we find this thing called pH. And you've probably heard of pH before. You probably have some familiarity with the pH scale. But this is how we actually calculate it. We take the concentration of H+ that we either found by being given it or being given the OH- concentration and finding the H+ concentration to find our pH. And that's how we do it. For numbers that are a little stranger, let's say my H+ concentration was 7.35 times 10 to the minus 4th molar. pH calculates in just the same way, negative log of 7.35 times 10 to the minus 4th. And if I plug that into my calculator, let me do it right now. We've got negative log of 7.35 times 10 to the minus 4th. I get myself 3.134 as my pH. Now, again, you might be looking at this and thinking, Professor Clements, you always told us at least in an answer have units, please. Turns out pH is one of the very, very few numbers in chemistry that doesn't have a unit. And so 5 as a pH is just fine. There's no units on it. 3.134 as a pH is just fine. There's no units on it. So if you're the type who forgets to write units down, this is your calculation. That's how we calculate pH. Now, how do you actually do it on your calculator? For most TI calculators and most kind of calculators that are a little fancier, you just type it as you see it. So take a negative, you hit the log key on a TI calculator. The log key, let me see, is this one right here. You can see that in green. And so you're going to hit the negative key. Now remember, negative is this one down here, not the minus sign. That says I'm subtracting two numbers, but I want the negative sign. So you're going to hit the negative log, and then you're going to type in your number. And as you type that on the screen, it's going to say negative log. The log actually puts in parentheses for you, so you don't have to type in the parentheses. That's what happens when you type negative log. Then you just type in your number. So if I had 1.0 times 10 to the minus 4th, I would type just like that. You can put a closed parentheses on it if you want to. You don't have to. The calculator will actually do it for you. And then you just hit the enter key down here, and it should tell you the answer. In this case is 4. So that's how you type this into the calculator. If you've got a calculator that's maybe not as fancy or a little bit older, like say this Casio down here, you're going to type it in a slightly different order. You're going to type your H+ concentration first, then you're going to type log, then you're going to type negative. I won't show exactly how that works right now, but that's what you'll be doing. So that's how you type those into your calculator in order to get a pH. pH and significant figures. When I said, hey, when my H+ was 1.0 times 10 to the minus 5th, I ended up with that my pH was 5.00. And it looks like I'm going from 2 sig figs. It looks like this is 3 sig figs. And you're saying, well, why am I changing the number of significant figures in my answer? And it turns out pHs are a little funny because they're a log, and the log has its own rules for significant figures. The significant figures in a pH are actually only the digits after the decimal, not the digits before the decimal. And so my sig figs here are only those digits after the decimal, but only for a pH, only for something where we took a log to get that number. So my 2 sig figs becomes 2 sig figs here. What's easier to remember is it becomes 2 digits after the decimal. 2 digits after the decimal. So if I had my H plus is 4.12 times 10 to the minus 11th molar, and I want to know my pH, I just take that, take the negative log of 4.12 times 10 to the minus 11th. I get 10.3851027 is what my calculator tells me, but again, we know better than to leave a number looking like that. What am I going to do? I'm going to do 3 sig figs becomes 3 digits after the decimal. The digits before the decimal don't count. So even though there's a 10 there, it looks like it has 2 significant figures. We're not going to count that. And we're going to say this guy is 10.385. Just so you're aware, on a quiz and test, there will be questions where you have to know how to do sig figs for this. So make sure you're aware of how to do that. So we had 10.385. Looks like 5 significant figures, but it's not, because we know it's a log, and only those digits after the decimal count as significant figures. How would we do it if we had an OH minus? If you had an OH minus, you'd use our equations from previous to calculate H plus, and then calculate the pH. So here's your turn. What is the pH of a solution with an H3O plus of 2.75 times 10 to the minus 11th molar? And, I got 4.2 times 10 to the minus 11th. I was awfully close to this one. I forgot what my sample problem was. So what are you going to do? Yeah, you're going to stop the video. You're going to try this out, plug it into your calculator, and see what you got. All right. 3 sig figs means 3 digits after the decimal. It's not this one. It's not this one. It's not that one. If you plug that into your calculator, you take the negative log of 2.75 times 10 to the minus 11th. You're going to get yourself 10.560. It turns out we can also take pOH. So pH was defined as the negative log of my H plus concentration. What do you think pOH is going to be? It's the negative log of my OH minus. The only reason people would really do this on a regular basis is because it turns out there's a little shortcut that says if you take the pH plus the pOH, you get 14. So some people will shorthand things and find a pH by going through this route. You don't have to do it. I'm not going to go through it in any detail, but I do want to cover what pOH is because the homework system for this class does actually use pOH. I am perfectly happy with you calculating pH given OH minus by going through H plus and then calculating pH. But you can also calculate pOH. Very similar calculations as we had before. And you can calculate pH from pOH or pOH from pH using this second equation. What about the opposite? What if we're given a pH and we want to find my H plus or my OH minus concentration? So let's say the pH of a system is given as 9.00. How can we calculate my H plus concentration? Well, we start off with the definition of pH. It's the negative log of my H plus concentration. And I'm going to do the algebra that shows how to solve this. You don't need to know how to do this algebra. You just need to know the end product. but I'm going to show it to you anyway. So it turns out what we want to do is we want to isolate that H plus. So we're going to put a negative on both sides. So I'm going to put a negative here and a negative here. Two negatives make a positive. They cancel out. And so I get negative pH is the log of the concentration of H plus. Now I want to get rid of log, but log isn't something like it was multiplied or divided by. It's a function. And what you do with a function is you do the opposite of it. So if my function was 1 over, then I just 1 over again, and 1 over x is x. Details aren't important. But the opposite of a log is a power of 10. And 10 to the log of something is just equal to that something. And again, you don't need to know this. I'm just showing it for those who are interested. And you end up with this equation. I'm just going to put the H plus on the left because that's how we see it most often, is that H plus is 10 to the minus pH. So if my pH was 9, my H plus is going to be 10 to the minus 9.00, like I had in the example above. And what you end up with there on your calculator should be 1.0 times 10 to the minus 9th molar. Your calculator's only going to give you 1, but how did I get 2 sig figs there? Remember when we were calculating a pH from a concentration, our sig figs became digits after the decimal. When we do it backwards, we also do the sig figs backwards. Our digits after the decimal become our sig figs. So we had 2 digits after the decimal. We now get 2 sig figs. And that's how we calculate an H plus concentration from a pH. If my pH was 12.942, my H plus would be 10 to the minus 12.942. I type that in my calculator, and I'll show you in just a second how to type that into your calculator. We get 10 to the minus 12.942, and I get 1.142878335 times 10 to the minus 13 sig figs. 3 digits after the decimal become 3 sig figs. And I get 1.14 times 10 to the minus 13th molar, even though I didn't have those concentrations in my formulas. Since I'm reporting a concentration at the end, I need to report it in units of molarity. So 1.14 times 10 to the minus 13th molar. How do you do it on your calculator? For most calculators, the 10 is just the opposite of the log. So if you look at your calculator up close, you've got the log key here. But right above that in little blue is a 10 to the minus, or 10 to the power key. And so what I'm going to press is I'm going to press second, then log, and that should give me something that says 10 caret. So let me do that really. 10 caret parentheses. Then I just type in my concentration, 4.0 times 10 to the minus, well, times 10 to the minus would be E, right? 4.0 E minus 3. And then I hit enter, and I get my answer, 4.0. Silly me. pHs. I was calculating pHs. pH here, 3.05. 10 to the minus 3.05. Minus 3.05 is, again, I'm going to put mine into scientific notation mode, 8.9125 times 10 to the minus 4th molar. What do I have for sig figs? 2 digits after the decimal become 2 sig figs. I get 8.9 times 10 to the minus 4th molar. So 10 to the minus is inverse of the log. You need to put that minus sign in there. It won't put it there for you. If you get a positive exponent for your concentration in an acid-base problem, you probably, but not definitely, probably did something wrong, because most of the time you should get negative exponents when you do these problems. Okay. If you have an older calculator, you're going to again do it negative, different. You're going to type in your pH, make it negative, and then take the 10 power of it. Your turn to try. If we've got an H plus solution, if we have something with a pH of 8.27, what is the concentration of H plus in that solution? You paused, right? You did? Yeah? Okay. Trust you. 10 to the minus pH. 10 to the minus 8.27. Plug that into your calculator. Let me do that. 10 to the minus 8.27. I get lots of digits. 5.3703 something times 10 to the ninth. I know it's one of these ones. But which one? 2 digits after the decimal become 2 sig fig. So I get 5.4 times 10 to the minus ninth molar. How about this one? What's the pH of a solution with an H plus of 1.55 times 10 to the minus fourth molar? Again, pause. Okay. Here we know that pH is the negative log of H plus. And so we just get the negative log of 1.55 times 10 to the minus fourth. Plug that into a calculator. Negative log of 1.55 times 10 to the minus fourth. You get 3.80966. But what do we have? 3 sig figs becomes 3 digits after the decimal. It's going to be 3.810. So we know that. What does the pH scale mean? Why do we calculate these pHs? Again, primarily historically because of convenience, but people are used to dealing with pHs now, and it's a little easier to talk about relative pHs than it is to talk about relative concentrations. But what's the meaning of the scale? The meaning of the scale just tells us a little bit about something and whether it's acidic or basic. It turns out if your pH is greater than 7, you have more OH minus than you have H plus in the solution. We call that basic. If your pH is less than 7, you have more H plus than you have OH minus, and we call that acidic. And if your pH is exactly 7, you have exactly the same amount of H plus as you have OH minus, and we call that neutral. And as I said, most of our experience is with things that are acidic, because things that are strongly basic tend to dissolve us, and we don't like that. Acidic foods might be milk. Some people think milk is basic, but it is actually mildly acidic. It's got lactic acid in it. Coffee, slightly acidic. Apple juice, tomato juice. Can of Coke, 3.0 pH. That's a really low pH. It's very, very acidic, but nowhere near the acidity of your gastric juices. That's your stomach acid, which has a pH all the way down to 1.6. The smaller the pH, the more acidic it is. So we've got something like gastric acid, very, very, very acidic. So the stuff in your stomach, extraordinarily acidic. In fact, when you drink a Coke, you're diluting the acid in your stomach. It's kind of funny to think. But it's true. When you drink water, you're diluting it even more. And your body's used to that. It's designed for that. Your body's designed to take in water and other beverages, including some that might be a little bit acidic, and that's just fine. On the basic side, you're going to find that seawater is actually slightly basic due to some of the dissolved solids in it. Ammonia that you might use for window cleaner is also slightly basic. And way down here at the bottom of the scale is Drano, which is sodium hydroxide. Very, very basic, has a pH of 14. Greater than 7 means it's basic. Less than 7 means it's acidic. All right. So that is our foray into the calculations for acids and bases.